Okay guys, in this video we're studying the wave properties of light, and by that I mean we would like to investigate what is a wavelength, what is a frequency, what is an amplitude. In particular, we're interested in wavelength and frequency. We're also going to look at, in terms of light, what the energy is. So the energy of light it's a peculiar thing, and it's related to what I talked about in the last video regarding the fact that light can be viewed as a particle. Okay, so here we have a wave. I've just sort of arbitrarily placed some units on here. This could be millimeters or centimeters or just whatever. So this wave is actually going to be propagating, but what we've done is taken a snapshot of it with the cameras of our eyes or what have you, and we're going to analyze it based on that frozen moment in time. Okay, so if we see the wave starts here at electric field is equal to 0, and then it rises up to some value pointing upward, comes back to 0, and then back down again, and then back up. This is in fact the graph of a sine function. And so waves tend to follow this pattern. Now, if we wanted to know what the wavelength is, then the easiest way to go about that is to say, if I go from the tip of the wave to the tip of the next wave. But notice that length, the length that's involved there, is not different than if we had chosen to put that at a different location. A better way to define this wavelength is that it goes from any part of the wave to the next identical part of the wave. So if we were to say, instead we choose the moment where it rises right there at electric field equals 0 and crosses the x-axis, to the next moment that it's rising and crossing the x-axis. Note that we're not talking about the moment when it's falling and crossing the x-axis, although you could also choose that. You would need to go to the next part of the wave that's identical to that. And notice that each of these, from peak to peak high or peak to peak low, or falling through the axis or rising through the axis, they're all equally the same distance away, because this is a repetitive graph. So we call this then the wavelength, and we give it a special Greek letter, lambda. Lambda is the Greek letter L, so you can think of it as a length. Now, the wavelength describes a length from one peak to the other, but the frequency is not measured in space, but rather in time. So the frequency asks the question, how many times does this wave, now that we're viewing it as propagating, how many times does this wave, when we unfreeze it, how many times does it hit the side of the screen per second? If we were to close your eyes at the beach and just listen to the waves hitting the shore, that's a perfect example of frequency. So for our wave, if we had our wave moving, it's going to be moving to the right, and as it moves to the right, you can listen in your mind, you can listen to the sounds that would be created every time the tip of the wave, the peak of the wave, strikes the box. So as we basically slam our wave into the box, listen to the clicks that I'm going to make when the wave hits. So if I'm moving really slowly, I go click, 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 and there's a certain rate at which they hit. If I'm moving much faster, then it's going to go click, 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 and even faster, click, 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 click. So you can see that the distance in time between the clicks, or the interval in time between the clicks, is really what we're talking about. Now we do measure that as not the interval in time, but actually the upside down of that. So what we actually measure is how many clicks per second, is essentially what we're saying when we say frequency. Now frequency has a different unit. We can use the unit of, let's say, meters to represent wavelengths, but frequency has the units of 1/2. Now we have another way to talk about that because that's a little bit cumbersome, so instead we'll say it is equal to something called a hertz. The hertz is the same thing as per second. Okay, so if I say that something happens at 10 hertz, then I'm saying that it happens 10 times every second. Now amplitude. Amplitude's much easier to understand because we can see that this wave rises to this level, and we can say that it falls to this level, and if we were to say that that goes up to an electric field strength of let's say 1000 or something like that, and then goes down to -1000, we would say that the amplitude of this wave is 1000. So amplitude is just basically how high up or down your wave reaches. Now, we don't typically view amplitudes in terms of light because it's much easier to talk about it in terms of power in wave packets. So that is the description of the features of a wave. Let's move on to talk about the equations that you'll be using here. Okay, now notice that the speed of the wave was very important, and that's going to be one of your most important features of waves, is how fast are they moving. So in general, for all waves, the velocity of the wave is always going to equal the wavelength of the wave times the frequency of the wave. This is for all waves, okay? Likewise, for light, this equation still holds. However, although light can have a unique wavelength and it can have a unique frequency, it may not have a unique speed in space or in a vacuum. It always has that speed in a vacuum. Now in the next video we'll start talking about how that speed and the features of light change when it goes into a material. But at the moment we can look at how the wavelength of light and the frequency of the light are related to one another. So we can give ourselves an example, and we may remember from the last video that the speed of light is 2.997 times 10 to the 8 meters per second. If we were to do that in 3 sig figs, which we kind of do in this course, that would fall to 3.00 times 10 to the 8, so you can usually remember it fairly easily by just saying 3e to the 8. Okay, so if we have 3e to the 8 meters per second, and we say a certain color of light, let's say red light. So if we choose red light and we have a wavelength of that light that we find, or we are told at least, is, let's say, 675 nanometers. That's about right for red light. So if we're at about 675 nanometers, then we can now find out what the frequency of light is. In other words, how frequently do the waves of that particular light, that color red, strike a surface when you get a wave of light. Okay, so the frequency of the light is then easily calculated by using this equation. All we have to do is divide out the wavelength. But remember, we're using SI units here, so we have 675 times 10 to the negative 9 meters. Don't forget to use your SI units. And I get that is 4.4 times 10 to the 14 hertz. That would be our frequency for red light. It's unique to the wavelength and frequency. That particular wavelength also has a particular frequency, always for light. So let's describe what the energy is for light. We've just looked at a case where we had 675 nanometers, had a unique frequency of 4.4 times 10 to the 14 hertz. We can go ahead and rewrite those. We had a frequency 4.4 times 10 to the 14 hertz. We had a wavelength of 675 nanometers. There is also going to be a unique energy. Now, the energy of light is actually defined according to the frequency. So the total energy of light is going to be, if you send 1,000,000 packets of light, then obviously that's a lot more energy than this person over here who's just sending like 3, right? So total energy, sure, you can get more energy by giving more packets of light, but each of these packets of light carries a specific energy with it. We call these photons. A photon is the packet that we've been talking about, or a light particle. So the energy of photons is given as a certain constant. I like to always throw these constants in a different color so that you can always remember, oh yeah, it's another constant I'm going to have to throw into my, it's on your equation sheet. A certain constant times the frequency of your light. Now, this constant is called Planck's constant, and it is given as, in SI units, 6.626 times 10 to the negative 34 joule seconds. So if we wanted to determine the energy of this red light that we were talking about before, we would say, well, we have our frequency. This energy is going to be 6.626 e to the negative 34 joule seconds times 4.4 times 10 to the 14, and we could write hertz here, or we could write per second if we want to. And I'm writing per second so that you'll be able to easily see that seconds and per seconds will cancel so that we get joules of energy left. Now, this isn't going to seem like a hell of a lot of energy, and a single photon is not a lot of energy, but it's actually much greater energy than what the air has to offer in terms of temperature. So in fact, photons carry a lot of energy with them if you allow enough of them to stack up. I get 2.92 times 10 to the negative 19 joules. Now, this is a pretty messy way to talk about energy, so we have another energy unit that we use. So we can either use joules, the SI unit, or we can use another type of energy called the electron volt. Now, an electron volt is not actually so bad once you get used to it. Basically an electron volt is the energy that is required to get a single electron to be accelerated over a volt of potential. Well, how do you convert it? Well, that's actually quite easy to do. A single electron volt, 1 electron volt, is equal to 1.6 times 10 to the negative 19 joules. Now, that's not a coincidence. That's actually the way that we set up the unit. If you always remember that it takes 1.6 times 10 to the negative 19 joules to get a electron to be accelerated over 1 single volt, which shouldn't actually be something that you have to remember, because we should be able to go back and look at our electrostatics theory, and the energy is always QV. Well, the Q here is the electron, and the V here is 1 volt. So the total energy there for a 1 volt parallel plate capacitor would be 1.6 times 10 to the negative 19 joules for that single electron. So this is the way that we construct our electron volts. It's actually a little easier to think about this in terms of electron volts. In order to get this in terms of electron volts, you would just need to multiplied by your conversion factor, which is 1 over 1.6 times 10 to the negative 19, and that will give you 1.82 electron volts. It's a much cleaner way to look at energy. Make sure that you check out electron volts in your text. If you practice them just for a few minutes, you'll have it down. Okay, so, and you should have this down, because if I refer to a 2 eV photon, you should know what that means. A 2 eV photon would then be double this in terms of joules, so it'd be 3.2 times 10 to the negative 19 joules. So 2 EV photons are pretty common. They're actually the most likely, somewhere around 2.2 to 2.1 is the most abundant photon that reaches the Earth from our Sun. So we definitely want to be able to use that language. Let's look at the electromagnetic spectrum. Now, I like this diagram because it does several things. Number one, what it does is shows you that as the frequency gets larger, the wavelength gets smaller, and as the frequency gets larger, the energy gets greater, and as the frequency gets smaller, the energy gets lower. Also, the wavelength, as the wavelength gets longer, the energy gets lower, and as the wavelength gets shorter, the energy gets larger. So you can see that here in the frequency bar and in the wavelength bar. Another thing that this does is gives you the extraordinary scale. So you can see here that we're going from frequencies of 10 to the 6 to 10 to the 7, right? So this frequency is going from 1 million to 10 million to 100 million to a billion, 10 billion. So it's not a linear scale, it is a logarithmic scale, which means that the scale goes from a frequency, well, let's talk about the wavelength. It goes anywhere from about 100 meters on the left side here, all the way down to 1,000th of a nanometer, and actually much larger than that, so about 1,000,000th of a nanometer. When it doesn't actually end. It just gets longer on the weak side and shorter on the strong side. But that's the scale that we're looking at here. It's rather large. And what I really like about this is, and it kind of makes you feel small as a human, here is the amount of it that we can see. That is the this little colorful little rainbow here on the black bar. That is the visible portion of the spectrum. So in fact, there's light surrounding all of us right now that we can't see. Some animals creep over a little bit more along past purple into what's called ultraviolet, for reasons that I hope make sense to you just by linguistics. And then infrared is the region of light that is slightly less energetic than red light. And one more reason that I like this graphic is that it tells you, because these wavelengths are different sizes, it tells you the types of matter that they interact with. So in the visible light spectrum, we really are talking about, as a matter of fact, it doesn't really, it's a little bit off, but in fact visible light definitely interacts with atoms. It doesn't necessarily do it in a very fierce way, but what it does is it toys around with where the electrons are on the atoms. It definitely toys around with molecules and the molecular bonds, which is why you can easily get hot in the sunlight, because the sunlight has, you know, quite a bit of visible light and slightly infrared light. All of these very tiny things on the orders of bacteria, all the way up to or all the way down to the size of molecules and atoms, is around the range where ultraviolet, visible light, and infrared light interact. Once you get to the order of, say, your microwave oven, that's when you're actually going into the region of microwaves, right? And that's why we choose that frequency to exert energy onto your food in a microwave oven. Now, If you get lower, you start to get to circuits which are a little larger than that, can actually use radio waves, and then or very powerful radio waves anyway. And you can actually get really, really big radio waves if you get even larger than football fields. So one of the really important features, radio waves are not in fact sound waves. Radio waves are just another form of light, just like red or blue, right? But what it does is actually incites motion of charges on an antenna in the opposite manner that we did in the first video. So when your antenna feels, and your cell phone does this too, when it feels a wave, a radio wave coming in on the order of megahertz or something like that, it causes the electrons to move back and forth, and that causes a small current, and your phone or your device reads those waves by reading the current signal. So we call it radio because we use those to transmit signals that radios then interpret as sound, but in fact they're light. So also interesting. Here, when we get to the visible light spectrum, you can see that red is the most or the least energetic form of light, and purple is the most energetic form of light, of visible light. And then once we get beyond that, it starts to get to where if we go much higher energy than visible light, ultraviolet light has a tendency to mess with the electrons and the atoms and the molecules on your skin in damaging ways if there's too much of it. Once you get to X-rays, they're actually less likely to interact with matter, but when they do, it's much more catastrophic because they're tearing the electrons off the bottom shells of the atoms. And then it can just get worse than that when you get all the way up to gamma rays. The fierceness of gamma rays, there's an incredible amount of energy in gamma rays. Most gamma rays do not affect matter or tissue, but if they do, then it causes a lot of trouble. That's why you don't want to be exposed to very many gamma rays. Okay, so this is the idea behind the electromagnetic spectrum, and hopefully it brings your curiosity and makes you wonder a little bit more about light, which is a really fascinating subject. And the next video we'll be talking about what happens to light and the features that we just talked about, like wavelength and speed and frequency, but when it hits a material.